Now let's take a look at some of the material component options that Chandler Concrete offers. Let's start with water. Mr. Kuhn's going to explain to us how important the amount of water is to the overall performance of the concrete.
Yeah, when you do a mixed design in concrete, consistency is the key, and that's consistency not only in the type of materials, the quantity of materials, but the proportioning. And so water is one of the ingredients. So
Hmm.
if you're dealing with a sand or a stone, and it is SSD, basically the material's in a condition where it's not going to need to be taking away any water from the mixed design, but it's also not going to contribute any water to the mixed design. Now, if your moisture on any of your materials are above SSD, what that means is it's got surface moisture on it, and that surface moisture is going into the mix design. So if you've got a mix design, for example, that's designed with 33 gallons of water, and the moisture component of the aggregate is bringing 10 gallons of water per yard into the mix, then I've got to subtract that from the batch water. Otherwise, I have excess water in the mix design. And
Hmm.
again, the key to strength and durability is the ratio of water to cement. So if I've got a mix and I'm batching it and it's getting the same amount of cement every single batch, and I'm varying the amount of water coming in from my aggregate source, and I don't adjust for that on the introduced water side, then my water portion is changing. My cement portion is staying consistent, but my water cement ratio is varying as the moisture on the materials goes up and down.
Hmm.
That lends itself to wild variations in strength and slump and everything else. So
As we saw,
we
yeah.
tend to adjust, and most ready mix producers have to. You can manually adjust by regularly checking your stockpiles, running a moisture test, and figuring out what that moisture is and setting it in your computer. Or you can live adjust for it, which we do at most of our plants on the fine aggregates. And what that does is there's a probe that's in the bin, and when the material flows across the probe, it measures the moisture and does automated adjustments as batches are being run. So we do that on sand because that's the most highly variable. It holds the most moisture on the surface. We don't do that regularly on our coarse aggregates because they tend to be, even when they're wet, relatively low amounts of moisture. I
Hmm.
mean, a percent and a half is a pretty high amount on a stone, but you can get 6, 8, 10, 15% moisture on the surface of sand. And if you go from that down to 3 or 4% on a relatively dry day, that's a huge variation and would make a big difference in a mix design.
Absolutely.
Next, let's have a look at aggregate.
So most ready mix produce facilities, and this is the case for most raw material driven manufacturing facilities, are located geographically as close as they can get to their raw material sources. In the case of our plant, we're in an area that has limestone as the predominant material, and if you look at all the bin selections, the majority of them all are the gray material, which is various sizing of limestone. So on the far side, the dump truck that we've got here has a load of 57s, which is a 1-inch material, and then it is broken down into various sizes based on crushing at the quarry. So the more you crush it, the smaller it becomes, and then you screen different sizes out to end up with a gradation or a blending of the material for the particular size that you're trying to sell. We use mostly 57s, and if you crush it all the way down to a sand gradation, it's what's known as manufactured sand. It's just a limestone sand, exact same material, very similar colors. Just one is a sand sizing, sand gradation. The other one is a 57 size, 1-inch top size. The materials closer to us here, a 68 is a 3/4 inch material, and then our 78s are about a 1/2 inch to a 3/8 inch material. Like I said, that's the most common material because freight is obviously a significant chunk of the landed cost of the material. So the most of that we can get into a mix, the better off we are from an economic standpoint. But there are things that you can do with other materials that you can't do with limestone. For example, in a paving application, you do not want the surface that you're riding on to abrade and or get scratched off or wear away over time. You're probably really familiar with the rutting that happens at intersections for asphalt. Now that's not an abrasion situation, that's actually where the material is giving way and the weight of the vehicles in the intersection are pushing it down, creating the ruts. And that's pretty common with an asphalt paving situation over time. The more traffic passes you make, the more you're going to get rutting. You don't have that problem with concrete, but what you do have is, especially at intersections, drive-through lanes, turning areas, the wearing away it's like taking a rubbing wheel and grinding it over time. And limestone is a soft material. So when you're designing concrete for paving applications specifically, and VDOT does this, they specify a non-polishing material, or one that does not polish, abrade, or wear off. So if you take the limestone out of the mix, what's left is this yellow sand, is a quartzite kind of basis sand that actually is somewhat local. It comes out of the Withville area, but it's 30 miles down the road as opposed to just a few miles down the road with the manufactured sand or the limestone.
So what's happening here? Is he just pushing it back, or is he actually going to take a bucket out?
No, he's pushing it in because the dump trucks can't get completely over the pile, so they dump as close as they can, and if it comes out of the bin, they push it over with a loader bucket.
So that all goes down into a conveyor?
Yeah. The underneath all of these tunnel bins is a horizontal belt, and our entire loading process for aggregates for our plant is automated, and it's run by an automated material handling system.
If we were to, could we walk up and have a look, or I guess I should get that guy?
I don't know what you'll see in there. I mean, the grates are being repaired for maintenance.
So if this isn't limestone...
Yeah.
Oh no, we gotta...
No,
What type of material is this typically? Also a quartz material, the larger 57 non-polishing?
Well, the non-polishing material comes down from the on the way to Withville. Mm-hmm. I'm not gonna be able to talk here with all this.
Okay.
We can go back over this way.
So you can load over here too, it looks like, on the right? Or load the conveyor? Is that another hopper?
Yeah.
Right there?
So this is a truck hopper, and basically if we're using specialty materials or things that we don't use in sufficient quantity to justify having a bin full of them, we can load loader buckets at a time directly onto the incline conveyor and put small amounts of it into the plant. That would not be a high volume type application. And a good example of that is at the Civil Engineering Structures Lab off of Plantation Road. They've been doing a lot of testing of materials, and they've had a lot of batches that are using materials or sizes of materials that are not traditionally what we would use here. And a lot of their materials we've been running into the plant in an overhead bin through this truck hopper. They've used granite materials that come out of our Danville area. They've used some different size lightweight materials that we wouldn't normally use. They've used number 9 material, which is about a 1/8 to 3/8 inch material. Just a lot of different combination of things that are not normal for our plant and the types of mixes that we ship. But we've been able to furnish those for those applications for the testing that they're doing by running those materials through our truck hopper.
All right, and I'm going to ask the stupid question I've always wanted to know the answer to. So the numbering system, it's not aperture size on a sieve. It didn't seem to correlate to the actual size. Can you tell me about the...
Well, I think, no, I can't tell you about it. So,
okay. Oh, thank
so
God.
you put me on the spot.
I thought it was just me.
I think when you get under a certain size, I think the numbers refer to the number of openings in an inch
right.
from a sieve. So, for example, a grading, a number 4 gradation or a number 8 gradation or a number 30 gradation refers to the number of openings in a linear inch that you would have But when you get to the stone sizes, I think they're more nominal, like a 5 and a 3 and a 2. I mean, if you will, a 57 is a blend of a 5 and a 7, and the 7 is smaller than a 5. And then a 357 would be a blend of 3s, number 3 material, number 5s, and number 7 material. And their ASTM has gradation requirements and limits for each size that is relevant for the particular material.
I will have to look that up myself, and I've always wondered about that.
Just to give you an idea, it's kind of inversely logical, if you will. The smaller the number, the bigger the material. So a 3 is bigger than a 5, which is bigger than a 7. Now when you come to blends, like an 8 would be smaller than a 5, but we use a 57, which doesn't make it a bigger number. It's just a blend of a 5 and a 7. So in that case, the larger number, or the smaller number, 5 and 7 combine to make a 57. But if you think of it as a 5, the 5 is a larger number than a 3, but it's actually smaller material than a 3. So then when you put the large 3 together with the 57, you make a 357. It ends up being a bigger material because it has the number 3 material in it.
Huh, okay.
So an 8, which is obviously a much bigger number than the other ones, becomes the smaller of the material, and a 9's even smaller. And then to get really wacky, if you go to a 10, which is actually a bigger number, it becomes smaller than a 9.
Oh my God.
But, okay, so with a non-polishing mix, you've got non-limestone materials being used. So we bring in the natural sand here from closer to Whitfield. It actually comes from off of Route 100 down below Dublin. This material landed on the yard or landed at the quarry would be similar in cost to the manufactured sand, but as opposed to a few miles away for ACO, this is almost 20, 25 miles away, so it's a more costly material for us to use. But the quartzite nature of this material is such that it does not polish or wear away like a limestone will, so this is fine for paving applications. The bin next to it that typically holds our non-polished 57 uses a aggregate, a 57 size aggregate down in the same area, in the Whitfield area. So the freight's, kind of similar to what we've got with the sand, but it does not abrade either. It's not a quartzite material, but it is a much harder material than limestone is. Now, there's nothing wrong with a soft material like limestone from a structural application. I mean, you're not going to wear it away in a column or a footer or anything like that. It's only if it has the opportunity to be abraded, like in a paving application. If it's not a surface that's going to wear away, you're not going to have any negative effects from using limestone. It makes a great structural aggregate.
Cool. Okay, and then over here we have...
Yeah, some of the other materials that we use commonly, the most common thing would be a lightweight aggregate, and this material over here is an expanded shale product, and this comes from down in North Carolina. So this material is much more expensive on a per ton basis and even in a per volume basis based on two factors. Number one, the freight from North Carolina as opposed to local freight drives the cost up, but also this is a shale material, and I would reckon that dug right out of the yard or right out of the ground and crushed like we do limestone locally, you will end up with a material that probably doesn't run a whole lot more than our limestone material. The problem is that's not the way it's used. It could be used that way, but it has much more beneficial properties if you then process it. And the way they process it is they take this material, they kind of pre-crush it, if you will, and then they put it in a rotary kiln, which is like a hollowed out tube, and they put it in the upper end of it, and the tube rotates and this material tumbles down through it, and they put high heat, they burn gas that comes up through the lower end. The elevated temperatures expand this product, and it's called expanded shale. Oh, wow. And what essentially happens is this stuff ends up looking like popcorn. So if you can see kind of closely, you've got all kinds of pores in there, just like you would if you took a kernel of corn and put it in your microwave and heated it up, the air pockets in there blow up under the heat, and then it expands, and this shale actually pops up and expands just like your popcorn would. Once it expands, they bring it out the lower end, gravity pulls it to the low end, they then crush this down and size it just like any quarry would their material. And what we use predominantly is a 3/4 inch size. That's kind of the structural aggregate that we use. The civil engineering lab has done some testing with some 1/2 inch material, and we got that in specially for them. But typically, this is the structural material we use is a 3/4 inch. Now, this exact same material, just like our limestone can be crushed down to smaller sizes, this material can be crushed down almost to a sand gradation, and a -3/8 size with a lot of fines in it is the exact same material, exact same source that we use on our block plant side that we make lightweight concrete masonry units out of.
Okay.
So the primary reason why you would use lightweight aggregate is either to reduce the weight or to get the other benefit that you get with lightweight concrete, which is resistance to heat transmission or fire rating resistance. And in an elevated slab application, if you've got people inhabiting the building above the slab and a fire were to break out, it would reduce the time, or actually extend the time that it would take for the heat to pass through to the other side of the structure. And so you get a increase in the resistance to the fire transmission. So for occupational safety, building slabs out of lightweight aggregate is a good idea. That's primarily why it's used in this area. But when you get into an urban area where they're building tall, high-rise structures, the weight reduction that you get will allow you to reduce the columns. And when you're building buildings, the usable square footage for the building that you're building is your sellable product. And so if you're going vertically and you've got large columns, you're cutting into your amount of rentable or sellable space. If you can reduce the sizes of the columns, then you have more square footage that you can sell or lease. And one way to reduce it is to cut the amount of weight that you're having to hold up. And once you do that, then you can reduce the columns. And so that's why you would use lightweight aggregate.
So another type of aggregate that Chandler offers is river rock, and it's used for specialized applications.
It goes into a mix that we call exposed aggregate. And basically, when you do concrete, you pour it out of a truck, it comes out, it gets molded into whatever shape you want based on the forms and or the process. You can vibrate it, you can push it around, you can do whatever you want, or you can float it out into a slab. And in the case of a sidewalk, if you put it into a sidewalk form and flatten it out with a float and then put a broom finish on the top, what you're seeing is the paste and the concrete, and it looks just like a cream colored regular concrete mix. But inside of that, you have no idea what the coarse aggregate particles are because you can't see them. If we put this river rock in instead of a typical limestone on the surface, it would look just the same no matter which material we use. The reason we don't use river rock on a regular basis is this material comes from the coast, and the freight getting it over here and the cost of it would be way higher than using our local available limestone. And there would be no compelling reason to spend that money just to have the color of the rock and the shape inside the concrete look differently, because you wouldn't see it on the surface anyway. But in the case of a exposed aggregate finish, which is exactly the process that's used for many of the sidewalks on the Virginia Tech campus, especially around Squires and other areas, if you walk along and you look down and you see that rounded brown surface detail, that is an exposed aggregate finish process. So what we would do is we would make concrete with this river rock as our coarse aggregate. At that point in time, it would come out to the job site and it would go in place exactly the same as it does with regular concrete. And they would put it in the sidewalk or plaza forms, and then they would float it out. And then they would sit there and they would wait for the mix to start to set up. As soon as the mix started to set up, they would then, either with a broom or a hose, they would kind of wash the paste off the top. And that paste, as it disappears, exposes the aggregate pieces. And then once they've washed that surface off, they let the rest of the concrete set and get hard, and then they'll put a sealer on it, and you will see the brown aggregate pieces, and that becomes the look of exposed aggregate.
Next, let's have a look at some of the cementitious materials offered by Chandler.
The right side of the structure, the metal structure overhead, is actually 3 hoppers, and those hold either our cement or either of our pozzolans. The most common pozzolans that we use here are either fly ash with a tanker going by that just delivered a load of fly ash, or we do use some slag, and those are the 2 most common pozzolans. Almost every plant has at least 2 overhead silos for the powdered material. Depending on the market, there could be a plant that only runs cement, and it may just have one overhead bin. A lot of times you'll see them that are, if they're set up specifically for an individual job, you would configure the plant just for the materials if you're going to run for that job. And the more bins and the more silos you have, the more costly the plant. So for example, if you were going to put an on-site plant to do a paving job and you were only going to use 1 sand and 1 stone and 1 cement, and the cement could be a blended cement. It could come with fly ash or slag already blended in, so you're running a pozzolan mix, but it's all coming in as a single product. You may set up a 2-bin, 1 silo plant, and that would probably be the least number of materials that you would ever put in for ready-mix concrete.
Now for the material you've all been waiting for, admixtures.
If you can cut the amount of water out and still not impact your slump and other properties, then you obviously are going to get a higher strength because my water cement ratio has gone down. So the way you accomplish that is through a water reducer, which is a chemical way of making the water more effective. So you add a certain amount of water reducing chemical and it may cut down 5% of your water. Well, that 5% translates directly into a boost in strength. And the cost of the admixture in traditional water reducers is less than the cost of the amount of cement that you would have to put in if you were trying to bump it by the same strength increase. So if I had 4,000 psi and I added a water reducer, I may end up with 4,500 psi. But if I went back to my mix with no water reducer and I wanted to get 4,500 psi, the amount of powder I would have to add would exceed the cost of what I did with the admixture. So in a basic everyday mix design, incorporating water reducer is a more effective cost way of getting your mixes created. So pretty much all of our mixes are formulated with some amount of water reducer in them. Now the water reducer, and the reason for all the different products that we have, the water reducer comes in multiple formats. It can be neutral to set, which is a basic water reducer, or it can speed the set up, which is an accelerating water reducer, or it can slow the set down, which is a retarding water reducer. So we've got about 4 or 5 different varieties of that for the application in the mix, and that's probably half of our containers in here have some version of that, either standard water reducers, accelerators, retarders, and they're all stored. The reason for the C container is that all of these admixtures have to be protected from freezing and thawing. And by putting them in here, we can run a little bit of a space heater and keep the chill out of them, and then you don't have to worry about them freezing.
That's pretty cool. So mainly water reducers, and are there other admixtures too?
Yeah, if you take the standard water reducers, accelerators, and retarders off the table, there is a specialty water reducer. It's called a high-range water reducer, and basically water reducers, as you increase their dosage rate, a basic water reducer can start to retard on its own. And if you don't want it to retard, but you want a lot of increase in either slump or reduction in water, you have to go to higher volume water reducers. And you get into a class of water reducer, which is called a high range water reducer. And those can be put in at larger dosage rates, and you can put a lot of them in there without affecting your set times, or you can put them in there and get much higher slump increases than a traditional mix design. So those are also known as super plasticizers. You may have heard mid ranges. That's kind of a middle of the road between a standard and a high range water reducer, but they're all kind of like variations of the same family, and most of those are neutral and set. Outside of the water reduction family and all those variations, the most common admixture that we use is an air entraining agent. And an air entraining agent is primarily put into a mix design to protect the mix from freeze-thaw durability when the concrete becomes hard. If you take water and freeze it, it expands. And if that water is inside of hardened concrete when it expands, that expansion process will break up the concrete from inside, and over time, the number of cycles that you go through the freezing and thawing action, it will expand the water and then contract, and then it'll expand the water and contract. And it's like, somebody inside the pores of the concrete just beating on the walls of the concrete. Eventually it's going to break it up. It usually starts at the surface because that's where most of the water is. If you're in an outside freezing and thawing environment and rain's out there, it's going to be wet at the top. That water will soak down into it, but the air temperatures and things, the most destructive part is the part that's exposed to the cold air and has the wet internal structure. You'll start to see those surfaces wear off, and over time it'll just be a continual destruction as it works its way through the concrete. Eventually, over long periods of time, you'll end up with nothing but a pile of rubble. So to protect against that, what you do is you place little air bubbles which act as shock absorbers inside of the concrete. So now, if you can imagine hardened concrete with no air in there, you got pores that go through there. The water gets its way into the concrete, it freezes, expands, breaks it apart. If you instead make the concrete with the same materials, but you add little pockets of air in the form of bubbles, then the pores are still there. When the water gets in there and it freezes, instead of it pushing against the hardened concrete and breaking it up, it'll push into an air bubble, which the air bubble is not going to hold water. It's got a membrane around it, but it acts like a bouncy ball. If you sit on a bouncy ball, you're going to compress it. The air bubbles that are in concrete, the water will push and compress it, and it relieves the forces that the freezing process is generating. Therefore, it won't break the concrete up. And you need about, in a 1-inch stone size, you need about 6% by volume of air bubbles in the mix design in order to have adequate protection. As your stone size goes down, smaller mixes take less coarse aggregate, which means there's a greater volume of paste. So you need a little bit more air bubbles, because what you're doing is putting the number of air bubbles relative to the paste. That 6% is pretty standard for a 57 or a 1-inch size aggregate. If you go to like an 8 or a 78, the volume ratio changes, and you may need to be about 7% by volume of air. So now the way those air bubbles work is we don't go grab a basket of air bubbles and throw them into the load of concrete. We put a liquid admixture in there, and it works just like the dish soap that you use at your house. If you take your sink and turn the faucet on, you'll see a bunch of bubbles being generated, but when you shut the faucet off, the bubbles are gone. If you squirt a little dish soap in there and turn your faucet back on, you'll still see bubbles, but when you shut the faucet off, the bubbles stay behind. That's all the soap that you get on the top of your sink when you're mixing. In a ready mix environment, when you put all the materials, whether it's in a central mix drum or it's a dry batch plant, and the rotation and the mixing process occurs, essentially what's happening is the materials are being folded over top of each other, and they fall down, but in the process they trap bubbles into the mix. Those bubbles, without an air entraining agent, those bubbles are coarse, and they work their way back out of the concrete pretty readily. You're always going to have some amount of air bubbles in there. It may be 1%, 2%. Those are called entrapped air. But as the moment you add an air entraining agent in there, the air entraining agent is basically a stabilizer. And so now the mixing process occurs. Instead of all of those bubbles quickly getting back out of the concrete, they stay behind because the formation of those has become stable, and those stable bubbles stay within the concrete. Now there's hundreds of different things that can stabilize air bubbles, and all of them act differently from a chemical perspective to create different sizes and different amounts of air bubbles. The admixture industry has formulated the air bubbles that we use, or the air entraining agent that we use, to create the right size and the right spacing and the right stability of bubbles
for it.
So in addition to the water reducers and air entraining agents, most of the other admixtures that we use would be considered specialty admixtures, and they come in a lot of different forms, and generally they're driven by the job as to our choice of them, and we don't always stock them. A lot of times we'll get them in specifically for a job in a mix. One example of that is a corrosion inhibitor, and a corrosion inhibitor is used primarily in applications like parking garages, where you're going to get a lot of chlorides either tracked in on it, or in the case of like water retention structures, there could be chlorides in the liquid being held in a tank, and then that may be an application where you would want to use a corrosion inhibitor. And so what you're doing, a corrosion inhibitor, is putting a product like calcium nitrate into the mix design, and that acts as a sacrificial element. So you would add a certain amount of the corrosion inhibitor, which brings a certain amount of the calcium nitrate into it. Mm-hmm. And that product just sits there, and when chlorides soak into the concrete, it is used up to combat the chlorides. Now there's a certain life expectancy. The more of that you put in there, the more chlorides can be attacked as they get into the concrete. And depending on the loading rate of chlorides you would expect to see in service, the amount of product that you put in drives a certain life expectancy. So if you didn't put anything in there, the chlorides, as they get tracked in or brought in to the surface, would start soaking in, and from day one you would start to work a timeline of that calcium being able to get to the steel and start the corrosion process, and you can project through modeling how long it will be before the steel that's in the structure would result in a failure. A lot of times, based on the cost of construction, that pathway to failure is so quick versus the cost of construction that you wouldn't want to build a parking garage and 5 years later you'd have to shut it down because the steel is corroded to the point of being unusable. Because the repair cost at that point in time, if you only got 5 years out of it, I mean, you would be constantly replacing things in your parking garage. So that's not a very viable construction process. So what you do is you put the concrete in place with this corrosion inhibitor, and then what happens is the chlorides are still coming in from day one, but there's a period of time before the destructive nature of the chlorides actually start to occur because you're delaying it based on how much corrosion inhibitor you're adding. So you can put a gallon in a mix, you can put 2 gallons in a mix, you can put 5 gallons in a mix, and that dosage rate pushes you out timeline-wise. So the upfront cost of what you're spending on corrosion inhibitor is buying you delay in years till the point where the destruction process starts to occur.
So how much time would it buy you, do you think?
The admixture sheets will tell you, that, but it's, it could be, 5 years, 10 years. It could, you could get a lot of it, but a typical dosage rate on chloride corrosion inhibitor would be, probably a couple gallons a yard or so. I've seen them as high as 3 to 5 gallons. It's really a function of just how much you're willing to spend up front. Mm-hmm. So corrosion inhibitors are one specialty admixture. There are products, shrinkage reducing admixtures. If you're doing flat work, one of the big challenges is the amount of surface shrinkage that you're getting. And you can change the water tension characteristics inside of concrete through an admixture that kind of defers some of the stresses that are building up because of the tension in the water bubbles. And so it reduces the amount of shrinkage just by putting it into a mix design. Mm-hmm. Those are specialty admixtures. Probably about 10 years ago, the admixture industry kind of went through really a rapid change, and the number of things that we can do nowadays with the use of admixtures is markedly different than it was when I first started with the business. So it's kind of neat. I mean, it's making concrete mixes is kind of like cooking. I mean, if you enjoy it, you can play around and create different things. There's a lot of different properties that you can get out of concrete by playing around with the types and sizes and nature of the materials and the ratios of the cement and pozzolans and admixtures. And admixtures have really kind of opened up the window to a lot of variations and a lot of things you can do now that you didn't used to be able to do.
Last but not least, there are a number of other things you can add to concrete to improve its performance as well.
So another thing that we use in concrete is a product called fibers, and they come in all kind of different variations. You can get microfibers. This happens to be a fibrillated fiber, and this is made kind of like an adding machine tape. It comes out in a sheet, and the sheet is you can see there the individual strands are held together, but basically the sheet is kind of slit cut as it comes out, and so each individual strand is interconnected. As they go into the concrete mix, they're kind of all stretched out like a netting, if you will, and they all link together, but it's three-dimensional reinforcing. So when you look at those fibers in a concrete mixture, you'll see vertically, horizontally, I mean, it's just kind of all mixed together throughout there, as opposed to something like wire mesh that is one layer, one specific location reinforcing, and if it's put in properly, it's generally okay, but if it is put in the way it's most commonly used, it's put into the form, you pour concrete on top of it, it goes right to the bottom. The finishers make a half-hearted attempt to kind of pull it up, but it's never put where it needs. So basically you're spending a lot of money on wire mesh that probably wasn't needed in the first place. It was put there to give somebody kind of a comfort level, but then you end up not getting the benefits. If we do it in concrete, it's three-dimensionally placed where it needs to be. There's a macro fiber which has a little bit of structural nature to it. It's still kind of a synthetic fiber. These things are kind of bundled. When they go into the truck, they spread apart and you get individual strands, but these are much thicker and do have a little bit better holding capacity than a microfiber. And then if you use steel fibers, the steel fibers come in all kinds of different versions. This is actually kind of called micro rebar. It's twisted and it looks like a small scale version of rebar. And it will provide actually some structural reinforcing to the concrete. So, you know, all of these different things can be used in different combinations, different sizing, depending on the application. In the case of the microfibers, they do a real good job combating plastic shrinkage cracking. So if concrete gets put into a slab and it is low humidity, high wind speeds, solar radiant kind of effects, all of that will take the moisture out of the surface of the concrete and it'll result in cracks occurring while the concrete's still plastic. If you put fibers in there, it'll combat that.
That makes sense. So is it harder to, I have had a little bit of experience trying to jackhammer slabs with and without mesh reinforcing. What does this do to demolition? Does it make
Well,
it
it'll
more
hold the
difficult?
pieces together really well. So it will make it more difficult to break out. I mean, typically when you break a piece of concrete, you end up with two pieces, but if you have reinforcing in it and you break it, you'll still have two pieces, but they'll be interconnected. And so it may break well, but it will be hard to get it away and break up and remove it because it's wanting to stay with the other pieces. So the main reason, if you put enough reinforcing and the right type in there, you'll get what's called bendable concrete. If you take it to the extreme, which means concrete when it gets loaded will deform, and then when it cracks it'll fail. But if you have reinforcing in there, when it cracks it'll stay together. And when you have bendable concrete, the initial crack will lend itself to additional loading, and in some cases you can get higher levels of loading after it's cracked than what the loading was on it at the point it cracked. So the residual carrying capacity, especially in areas like earthquake zones and things like that, are really, really good areas where they want a lot of that reinforcing.
Interesting. So what do you think is in store for the future of the concrete industry?
Well, the big challenges for concrete is, you know, the greenhouse gases from the production of cement. So anything we can do or the industry can do to reduce the amount of cement that is used, it's better for the concrete, both from an environmental standpoint and from a cost standpoint, because concrete or cement typically is one of the most expensive materials that goes into a concrete mix. Blends of cements with pozzolans or new chemical technologies that let us use less water to get the same properties out that you would have without the technology. That's kind of where one direction I see the industry going. The other thing is to figure out ways to make the concrete perform in manners that it didn't used to perform. A lot of the reinforcing that we talked about does that. So it's just, you know, there's a lot of outside agencies, outside industries that are evolving themselves to allow for more beneficial properties of concrete, and the chemical industry really has changed in the last 10 years and allows us to do a lot of things with concrete that we couldn't do previously.
It sounded too during today's tour like the accessibility of different types of aggregates can influence the cost of what you're doing and what's appropriate. But
Yeah, commonly you would use local aggregates because concrete is a desirable material based on its low relative cost as a building material. The more you start taking the local materials out of the equation and you start bringing in specialty materials, you're definitely going to increase the cost. But in the case of lightweight aggregate, which we spoke about, you couldn't do some of the things with lightweight aggregate. I mean, if you wanted a 2-hour fire rating and lightweight aggregate lets you put a 4-inch slab in, I may be able to give you a 2-hour fire rating. With conventional concrete, it might be 1.5 feet of concrete. Well, you're not going to build in those kind of things. So that's an example of where changing the aggregate, even though it comes at a cost, would give you properties that you couldn't otherwise get with local materials. So that's kind of why you would spend the money on that. Otherwise, I mean, I could take lightweight aggregate and make 3,000 psi footer concrete as just as good as I could take limestone aggregate and probably charge you $50 more a yard for the concrete. And in a footer application, it would work well under either one. Why would you spend the money for lightweight aggregate?
Exactly.
So.
Exactly. So any last words of wisdom for people getting ready to go in the construction field?
Well, if you're in the business of being in the determination sector that's going to figure out what kind of concrete you're going to use, I would suggest that you reach out to your local ready-mix supplier and get somebody involved and let them help you, because concrete's a very versatile material. And if you want anything other than just a cookie cutter commodity product, then working in partnership with your supplier will be the best way to achieve that.
Sounds great. Well, thank you very much, George Kuhn, for the
Thank you.
detailed 2-day tour of Chandler Ready Mix.